Right, the next thing we're looking at is sketching the graph of the derivative. So we've already kind of touched on it. So when we're obviously dealing with strictly increasing and decreasing, there's certain points we want to look at, or certain situations where we'd need to know what the graph of the derivative looks like. But this is more based around when we have the graph of the original function, not necessarily knowing the equation, and we want to draw the graph of the derivative based on that. So the point is, if we know the graph of the original equation, what we know is where obviously the gradient is positive and therefore negative, and obviously the points where it changes gradient. Okay, so in other words, where it's stationary. So we use these three facts to help us obtain a graph of the derivative. Okay, so using those three facts, we've got them written here. So if we have a stationary point on a graph of fx, then on the graph of f dash x, this will translate as a point on the x-axis. In other words, we know that if obviously it's a stationary point, then the derivative will equal 0. So rather than a graph of x against y, this is going to be a graph of f dash x against y. Okay, so it's going to tell us where, as I say, what's happening in terms of the gradient. So we're using these three things. So in the second one, if the graph of f of x is increasing, so in other words, it's going up at any point, this translates into a graph of the derivative as being above 0. In other words, the derivative is greater than 0, is positive, and therefore if the graph of f of x is decreasing at any point, in other words, the gradient is negative, on the graph of the derivative, this will be below the x-axis. Okay, so using these bits of information, we can piece together a sketch of f dash x. So this is the kind of situation you'll get. You'll have a wee graph, okay, and it'll just say something like the graph diagram shows the graph of f of x. We want to find the graph or draw the graph of f dash x. So we don't know what the equation is. We don't really care what the equation is, but we're just going to use everything that's here to help us. Right, there's a few things in here that's kind of put in to mislead you in a way. Okay, so the 3 and the 7 there don't really translate as anything in terms of the graph of the derivative. So they're the roots, but in terms of what that means for the derivative, it's nothing. Because remember what the derivative is showing us the rate of change. So we need to take the gradient from this and the gradient at the different points and translate that onto our graph of f dash x. Now, the easiest way to do this, okay, is to almost draw a graph underneath, okay, a set of axes underneath, and translate all these different facts onto this graph. So the best place to start is with your stationary points. So what the stationary point on a normal graph translates as onto our graph of the derivative is a point on the x-axis. In other words, it's when it's equal to 0. Okay, so we can take these points, okay, and we can rewrite them on our graph of our derivative as points on the x-axis. So exactly the same with the other one. Okay, and then we're basically going back to this graph and we're looking at what happens kind of either side of the derivative. Okay, so or either side, sorry, of the stationary points. So before this stationary point, the gradient was increasing. Okay, in other words, it's positive. Okay, so what that tells us for the graph of the derivative is that before this stationary point, we'd be above the x-axis. So it translates as a line like that. So it's starting above the x-axis, but we know it has to come to this point. So it's obviously going to come down to this point. Right, so then we've also got increasing after this stationary point. So after this stationary point, we can see it's increasing again. So once again, it's going to be above the x-axis here. Okay, so we draw a line like that. And then what's happening between the stationary points is that the gradient is decreasing. Okay, so it's getting smaller. Okay, in other words, it's negative. So in which case, on the graph of the derivative, it will be below the x-axis. But given that we know it crosses the x-axis of these points, we know it has to come from here and go down here somewhere before coming back up. In which case, you can kind of imagine what it would look like, hopefully. Once I let this finish, it goes like that. Okay. So there's little things you can use for clues. You know this hopefully by now, at some stage at least, you'll know this is a cubic. When it's got that shape, it means it's x cubed. So when we differentiate, we know it's going to be x squared. So we knew in advance it might look like that, but we're using the different parts of the gradient to help us with it, okay? So one more here. So again, we're more focused on the stationary points. Don't worry about this point here. This is not necessarily meaning anything. It's the stationary points and the points and what the gradient is doing around those stationary points. So start by drawing your set of axes and then translate the stationary points down, okay? So what the stationary points mean is that the gradient is 0, in which case the graph of the derivative, they're going to be on the x-axis. So we've got that one. And we've got the 2, 3 as well. That's going to be on the x-axis. Okay. So then, in terms of what's happening before and after and around these different stationary points. So before this first stationary point, we can see that the gradient is increasing. So what that means is that we've got a positive gradient. Okay, in which case it's going to be above the x-axis. But again, it's going to have to come to this point. So it's starting high and then coming down to this point. Right, it's also increasing thereafter. Okay, so after the stationary points, we've still got a positive gradient. So that means once we hit this point in our derivative, we still have to stay above, we have to go back above the x-axis. Okay, so it's going to come back up, but again, the next point we know it crosses the x-axis is this point. So it's above the x-axis and it's going to have to come back down to this point. Don't worry about the height, just as long as you're showing that it's kind of hitting this point and not going below, okay, coming back up and then hitting this point. But then after this point, we can hopefully see that the gradient is negative, okay, in which case on our graph of the derivative, we're going to be below the x-axis. So we should have a graph that looks like this for our graph of the derivative. Okay, so it's just, I think there's a lot of things there to kind of confuse you and not mislead you, or but the point is that you might be misled by them. So focus on the gradient. Okay, that's what we're looking at here. We're not necessarily focused on the points where it crosses the x-axis. Yes, we were looking at this one, but that was because it was a stationary point. Just remember the stationary points translate as points on the x-axis, and then you've just got to kind of fill in the gaps. Don't worry about how far high this goes. That's not what we're looking at here. We're just looking for the shape of the graph.